The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
At this time, I'd like to introduce Gabriel Carrera. I may be saying it, okay, and Stephen Foster for their presentation.
Good afternoon. My name is Gabriel Carrera. Stephen Foster and myself are going to be presenting on the Lee County Courthouse project. Before we get started, I'd like to share a brief video with you.
During the 1880s and 1890s, through the turn of the century, the early 1900s was the golden age of courthouse construction in Kansas, when all of these kinds of buildings were constructed in all counties all over the state.
They are by themselves one of the largest collections of Victorian architecture anywhere in the United States. I think the reason that the counties built these ornate courthouses was to lay the statement. The writer described them as the cathedrals of the prairie.
As you can see, there's a great significance in these courthouses. In early 2000s, then Governor George Bush created a commissioning courthouse program, which basically funded repairs of structures such as these. Lee County was among the first courthouses chosen for repair because of its history of distress. WJE came on site in 2008. Just a brief overview of the structure. It's symmetrical in nature. The perimeter of the structure has a continuous masonry spread footing. The foundation floor is 6 wise, and it supports approximately 40 feet of 4 wide masonry. This is a typical floor plan. Basically, the structure has a central core, the stairway, which has connecting arches out to the wings and arches in between the wings, as shown there. The second and third floors are much of the same, similar floor plan. However, of significance is this grand courtroom and balcony area found on the south, as shown here. The significance there is that the third floor diaphragm is basically missing, so there isn't as much stability, and that'll come into play later on in the presentation. Here's a little bit more information on the elevation. The south portico corresponds to the grand courtroom and balcony areas, and you can see the roof lines up with the remainder of the roof of the structure, and the northern porticos are one level below. The structural system, as you can see here, it's load-bearing masonry walls supporting a system of I-shapes and upturned channels and a slide arch, a cindercrete slab that's reinforced with heavy wire gauge mesh. When we came on site, we saw multiple forms of distress. Distress included stair-step cracking of the stone, masonry, interior there, the interior arches, finishes, plaster finishes. Here's just an elevation of the typical distress we saw. Please note there's There's cracking at the archways, at the windows, and just all over, really. An area that we kind of noticed was the balcony location. We saw that the baseboard had separated from the exterior balcony wall, or the exterior wall at the portico. Some of the wood frame members had withdrawn from the exterior wall, and so what we did was we did a total station survey, and the results are as follows. We found that the out-of-plane deflection at the roof level was up to 1.6 inches, and it lessened as it went down to the base. Other issues included deteriorated joint sealants at the perimeter, ponding water, and clogged area drains. And now Stephen will continue with the presentation.
So as we continue with our assessment, one main task we wanted to perform was a geotechnical investigation, and what we found was we had natural fat clays on site, which are common to Central Texas. We performed 7 different boring locations, one from the interior core of the building and then the rest around the perimeter, either interior or exterior. And what our geotechnical engineer told us was we had a medium to very high shrinkage and swelling potential with various levels of moisture fluctuation. And what we found was our interior boring showed low moisture contents compared to our exterior borings showed higher moisture contents, and we also had a different liquidity index of the soil. So we had different soil basically between the inside and outside of the building. So the question was, what's going on? Obviously, we've got all sorts of distress. So what we determined was we had this relatively stable central core, both from the inherent construction with that central stairwell and also stable soil compared to our perimeter. Again, with our arches almost acting as hinge points to our structure, when that natural fat clay would expand and contract due to the moisture, we got differential movement of the foundation, which resulted in the cracking of the walls, which was a result of our unreinforced masonry footing being unable to distribute those differential movements between the soils. And the out-of-plane wall movement that Gabe referenced on the portico wall, also a result of that shrinkage and swelling of the soil and localized movement of the footing. So how to fix it? And particularly, our approach had to account for these various challenges. As Gabe mentioned, it was a registered historical landmark, which meant our repairs had to be consistent with the Secretary of the Interior standards. The courthouse was going to remain open throughout the process, so we had to take into account all the various considerations. The employees were constantly indicating movement. It was got to the point where we felt like they were saying the sky was falling every other day, and it got to be the boy crying wolf to some extent. But obviously there was movement going on, so we had to accommodate all those various activities and several unforeseen conditions, as we'll get into. So partly because of the employees, but also for our own security and comfort, we installed a couple different monitoring systems. First, we used just simple crack gauges at locations based on the tenant's indications of where continued movement was occurring, but also in areas that were specific to the structural consideration. We would monitor those during our site visits throughout the course of construction. And we also used a real-time monitoring system during the course of our repairs, as you'll see when we get into the repairs and how we excavated underneath the building to monitor should anything get beyond preset limits. We used LVDT sensors to monitor deflection and also tilt sensors to monitor rotation of the walls. So the question was, what do we want to do with the perimeter footing? And we considered drilled shafts. Our geotechnical engineer recommended 25 foot deep, but really that was tossed out the window for the same reasons. We wouldn't be able to transfer the load across that brittle masonry footing. So we quickly went into designing a continuously reinforced concrete footing, and which allowed us to take into account the benefits of the arching action of the masonry. When we excavate a particular section to put our new underpinning in, that load will be distributed due to the running bond of the masonry, and then we could move around in a hopscotch-like pattern to put in our underpinning segment. Our design was 2.5 feet deep with 6 feet wide. We had 12 number 6 bars, longitudinal reinforcement, top and bottom, and quadruple leg stirrups, number 5s at 10 inches on center. And as I alluded to, we followed a leg and leg approach, which really meant we would excavate a segment. Our segments were 6 foot, which was determined by the arching action of the masonry, but also by the lap lengths. It's a combination of the two to determine what size bars you have. We'll determine what lap length you need, and also working that with how much the masonry can span. So we would dowel in our adjacent reinforcement for the next segments. We tie in our lap reinforcement to the longitudinals, and then put in our stirrup cage, cast our segment. And we also did a grout strip detail at the top, which we'll talk about in a minute. That was to promote bonds between the masonry footing and our underpinning. So you see here the typical excavation. The reinforcement cage is in place. We've cast the segment, excavation has started, and then this is your dowel reinforcement when the excavation is complete. Our grout strip detail was 2 to 4 inches in the field is what they ended up using typically. We pumped that with a non-shrink grout material to promote a good bond line. Our typical mix, we were concerned that we may get too much shrinkage and separation at that bond line. And here you can see when we excavate the next segment, it was cast tight to the masonry footing. Another detail to consider was at the corners. We couldn't capitalize on the benefit of the arching action, obviously, at the exterior wall. So our approach was to essentially cut the corner in half, excavate 1/2 at a time, dowel the same type of reinforcement. What the contractor elected to do was to shore 1/2 with a series of needle beams you can see here. So you'd excavate, shore, excavate the other half, put in the whole segment, cast it. This was another way our grout strip was able to be a benefit to us. We could cast the whole segment and then split our grout strip placement into half. Once the first grout strip met our strength, then he could remove the needle beams and cast the next segment. So as Gabe alluded to early on, there was an underpinning performed in 1911. You can see here the original masonry footing, and then a concrete footing that was installed in 1911. We understood it to be at the southwest half of the building, as indicated here. So in our design, we knew we had to account for stepping underneath that 1911 footing. You can see here we really have 2 corners, an interior corner, an exterior corner, and a step. We've got our lap lengths to get our continuous reinforcement top and bottom, our hairpins to close the corners, some of the detailing that was involved in our original design. When we got out on site, however, the entire span of that 1911 footing was completely voided out. It appeared that the contractor had excavated from the interior, excavated from the exterior, poured concrete from either side, and it never consolidated to the middle. I didn't bring a better photo, but you can see here some of the square ransom bars that the previous presenter talked about. There was some reinforcement in there as well. So our approach then changed. Rather than our original leg and leg approach, the first step was to repair those voids. And what we did was just treat that as a compression element to continue to get the load down to our new footing. So we put some temperature and shrinkage steel into our opening, tied that to the existing square bar again, if you could see one here. There was some had more than others. Place it again with a non-shrink repair material, and then continue with our new underpinning, which created for a lot of detailing and field conditions and changes. It was a complex process for the contractor and for us in the field. We had areas where we had steps, as I alluded to in our original design, but there were also additional steps due to the presence of the footing in places we weren't expecting. We had areas where we had a step and a void. We had areas where we needed to demo out the 1911 footing to accommodate certain things. The curved portico walls that you saw earlier, our underpinning had to follow that as well. So a lot of challenges, but ultimately, as we talked about earlier, the changes between the historic concrete and what we're able to do today with modern day construction practices, we were able to provide a uniform, stiff perimeter reinforced concrete footing. So we also took into account the wall stabilization for that south portico wall, and Gabe's going to talk more about that.
All right, thanks, Stephen. Upon completion of the foundation stabilization project, we focused our attention onto the walls that we had noticed had out-of-plane deflection. So we knew we had to stabilize the walls back to the central core because that was the most stable portion of the building. At the roof and at the balcony level, we were able to use tension rods to transfer that load or at least maintain it in its place. However, on the second floor, because of historic finishes and such, we decided to use a different approach. The approach that we used was to use the existing structure. So as you can see here, there was a existing I-shaped beam that we decided to turn into a tension type member. And what we did was we attached to the exterior wall using clip angles and post-install anchors. We welded to the I-shape there, and then we installed a concrete beam. The concrete beam extends from this area here to the exterior wall. We doweled the northern area here back to the wall on the interior of the courthouse and doweled here at the exterior. This cross section here shows what we had to do to get into that area to pour that concrete beam. We shored the second floor that has the courtroom above. We demoed about 3 or 4 wides of masonry wall, and then placed that concrete, as you can see there. This is the finished product. That concrete beam spans as shown previously, and this angle here basically completes the connection for the tension tie from the exterior wall to the concrete flexural beam. All we did was weld a clip angle and post install into the concrete beam. That's basically the finished product. As you can see, we use concrete to provide a flexural stabilizing member, and we were able to conceal it. Now, in summary, we've used different concrete elements to strengthen and stabilize the courthouse. However, how are we sure that it worked? Well, as you can see here, this graph indicates the total movement of six crack gauges that are located throughout the courthouse. The horizontal axis is time. During the underpinning project, as you can see, we started collecting some of our data. The main areas here, this is when construction started excavation, and right after excavation we experienced a rain event, and that's when we started seeing this building kind of start moving. Different spikes indicate different areas of excavation as well as other storms. Now, after the stabilization of the foundation was complete, we performed the lateral stabilization, as I mentioned, and we kept monitoring the structure, and it appears, I guess, by the data that we've stabilized this cathedral in the prairie. And that concludes our presentation.
How do the contractors handle surprises about consolidation and bid?
Change orders.
Yeah, there was definitely a price battle, so to say, between the owner and the contractor. But yeah, maybe I should leave it at that. But more or less, I mean, that was our once we established the first approach. Really, the problem was when we excavated our first segment, and we thought, oh, we've got a local void here, because again, we're sticking to our 6 feet. It was almost like one at a time, and the way he was working, he kind of had one side of the building doing a little bit of work and the other side of the building doing a little bit of work. So we didn't know if it was all going to be voided out. And then as we opened up each one, the approach kind of became, solidified, and then say, okay, we can do this for everywhere. But at first, we didn't know, if it was just one local fix. And he provided, to get more specific, he provided a price thinking it was going to be just kind of a one-off thing. And then when he realized it was going to be everywhere, we kind of had to work with him and adjust. Yeah. Yeah. Any other questions? We may have time for one more. Sure.
Are you going to do the same thing with all the other courthouses?
We're trying to. The ones that have problems, Gabe's lined up to do the underpinning, similar underpinning at one of the other courthouses.
Would it have been cheaper to tear the building down and build it?
You know, that was one of the, we didn't mention it, but a previous consultant to the county had recommended that as the only solution, to tear it down and build it again. But I don't think it would have been near as expensive to do what we did, and obviously to preserve the historic.
You did it cheaper?
Yeah, I would think it'd have to be. Wouldn't compare. The underpinning cost was about 1.2 million, somewhere in there. So I don't think they would have been able to rebuild the whole courthouse for that. And obviously preserve the historic nature. All right. Thanks.